Hello? 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 Testing 1, 2, 3. Testing 1, 2, 3. Testing again. 4, 5, 6. Testing 1, 2, 3. Testing again. 4, 5, 6. Hello. Okay, I'm peaking. Am I peaking? This is absurd. ABC. Testing again. 4, 5, 6. Hello. Okay, I'm peaking. Am I peaking? This. Alright, so hey guys, what's up? It's the Culture Man here, investigating your favorite everything, and today I will be studying chemistry. Yay! So this is the first time I've ever done a live stream like this, where I screen record while simultaneously using my webcam, my shitty low quality webcam in my laptop. There's a black bar at the bottom of the screen. I'm sorry about that. That's out of my control. I'm using a window capture, so it's capturing my Word file, and I don't know how to make it full screen, so it is what it is. It's also experiencing like a whole minute of latency, so I can't do anything about it. But anyways, this is quite special because I've been meaning to do this for a long time. I've been thinking about doing this for a long time. Studying is a thing that I've been doing for the last 14 years of my life. And right now, as far as chemistry goes, I've come to an end. Tomorrow I will have my chemistry final exam for my chemistry course, Chemistry 11 in my college, aka General Chemistry. And not only will it be my last chemistry course in this semester, but also in my entire college and university experience, but also in my entire life. So after this final exam, I will never in my whole ass life study chemistry again. This is the last time. Me and you, Mr. Chemistry, me and you, or Miss Chemistry. I'd like to think chemistry is a woman. All right. Is it working? Entire life. So after this final exam, I will never in my whole ass life. Okay, what is happening? I am studying chemistry. That's right, because I have final exams tomorrow. All right, so as expected, chemistry in the USA is way easier than studying chemistry in Hong Kong. And even though I've already taken Chemistry 10, which is Intro to General Chemistry, and Chemistry 11 in college, neither of these courses even touch on organic chemistry or inorganic chemistry for that matter. So this is actually easier. Some parts of Chem 11 is tougher, but in general, this is actually way easier. Like, it's fucking stupid. The chemistry I studied back in Hong Kong 3 years ago is 10 times tougher. So, American education system, what are you doing? But anyways, no complaints. The easier the better for me as a student, because I'm going to get an A, or at least a B, because I didn't actually really do too well in the exams, at least the first few ones. But yeah, I'm just going to go over my notes, the notes that I've written for my class, and just talk about it really live, so you guys can react to it as well. Fuck. I love my Wi-Fi. The easier the better for me as a student. I love my Wi-Fi. My Wi-Fi is going strong. Spectrum. Alright. Here is the table of contents. Only 10 chapters. So without further ado, let's do chapter 1, Introduction. The scientific method. Of course, every single science-related class has to start with the scientific method. And every single course and every single textbook has a different definition, but it all generally goes the same. You observe something, you ask a question, you have a hypothesis, and then you do something about it, like maybe an experiment, and then the experiment yields conclusion, and enough conclusion becomes a law, and that's the gist of it. Measurements and significant figures, which is something that I've already learned about 5 years ago in math lesson in Hong Kong. Not math class. Don't get it twisted. It's lesson, okay? Just measure, dude. The students of this class, my classmates, are in their late 10s, early 20s. Some are even probably in their 30s. And we're still learning about how to use a ruler. Are you serious, America? But measurements. Use a ruler. Everybody should know how to use it. Significant figures. Everybody knows what are significant figures. But when you multiply or divide, use sig fig. When you add or subtract, use decimal counts. That's just what I'm saying. So, 3,400. 1 sig fig, it's 3,000. 3,500. 1 sig fig, that's 4,000. All right. Precision, accuracy, and outliers. So we got the standard deviation, we got the percentage error, we got units and metric measurements. Oh, America moment, because Americans use imperial units, which are actually stupid. Metric units are the best. That's the fact. Yes. Then we have unit conversion via dimensional analysis. This is another really stupid thing. Dimensional analysis. To convert... Okay, I know this doesn't mean anything, but okay, you know what? Instead of talking, let me just perform it. So 1 kilogram to... I don't know, milliliter. That does not work. Shit. Kilogram is mass. Okay, shit. Screw it. 1 kilogram to 1 gram. 1 kilogram to gram. Okay? How do you go from 1 kilogram to gram? 1 times 1,000, right? Now, okay, let's do the reverse. How do you go from gram to kilogram? Obviously, divide 1,000. So if it's 1 gram, then divide 1,000, then 1 over 1,000 kilogram. Easy as that, right? Simple. But for some reason, a lot of American teachers do this, where instead of 1 divide 1,000, they do 1 times 1 over 1,000. Which is the same, of course. But and here you think, oh, it's just times 1. Doesn't, it's simple. It's not a huge difference. But in an exam, when you're stressed out, when you don't have a lot of time, and you're dealing with tons of different numbers, this will just bog you down. So instead of adding another fraction and another fraction and another fraction, just compress it. It's way easier like that. All right, measuring volume, you know the drill. Liters, milliliters, centimeters cube. Centimeter cube is a milliliter, right? Right. Density is mass over volume. Temperature, I personally use Celsius. Right now it's 17 degrees Celsius. I don't know what's Fahrenheit in Fahrenheit. Nor does it matter all that much because the temperature just changes so much in LA. Like, I realize back in Hong Kong, we really care about temperature. Oh, it's 23 degrees. Let's wear a light jacket. Or let's not even wear a jacket. But in LA, it doesn't matter because it can go from like 15 degrees Celsius to like 30 degrees Celsius within the same day. It's insane. And finally, we have describing matter and its changes. So elements, compounds, and mixtures. Everybody with a brain knows what that is. Elements are elements. Compounds are just a bunch of elements, and mixtures is just a bunch of compounds. Physical properties and chemical properties. So, easy peasy. Chapter 1 is over. Done. Can you show me a quick glimpse of everything because I'm really curious, but I have to go. Here is everything. Okay, it gets really complicated and difficult at the end for some reason. But in the beginning, it's super easy. All right. Right. Chapter 2, Molecules and Nomenclature. Atomic theory of matter. So basically the history of atoms. Oh, Socrates believed that everything's made out of fire, water, whatever. That kind of shit. Fundamental mass laws. So mass conservation. So, wow, you can't create something out of nothing. What? Who would have thought? That is insane. Chemistry is so difficult. Oh my god. Definite proportions, atoms, ions, and isotopes. So atoms are made out of protons and neutrons in the nucleus, and then electrons surrounding it, and plus or minus the electron, ions. Plus or minus the neutrons, isotopes. Protons stay the same. Simple as that. Elements in periodic table. Easy. Compounds, easy. Nomenclature, easy. Acid nomenclature is a little tricky, so there's this incredibly stupid slogan. I ate something icky, I bite something delicious. So 8 acids. So nitrate becomes nitric acid. So nitrate is, I believe, NO3 minus? Hold on. Yes, it's NO3 minus. Thank God. Yes, it's NO, because A is usually thicker. I is a little thinner. So sulfate is. Hello? Hello? Yes, it's NO3 minus. Thank God. Yes, it's NO, because A is usually thicker. I is a little thinner. So sulfate is. Oh. Hello? God. Okay, I don't know what's happening. My Wi-Fi is breaking apart and I love that. Alright, nitride hydronitric acid. That is not a thing. Is that a thing? No, what? Oh, it's a thing. Hydronitric acid. Is that HN? Oh, HN3. Duh, because N3. Okay, yeah, okay, I get it. I get it now. Alright, chapter 3, molarity. So atomic mass and mass spectrometry. It's so weird. Why would you suddenly talk about mass spectrometry? Mass spectrometry is so much more difficult. Formula, mass, so bonds, moles and molar mass, percent composition, empirical molecular formulas. So, you know, oh, there's a compound, there's a CHO compound, there's a this percentage of C, this percentage of H, this percentage of O. So C over, you know, 12, H over 1, O, whatever percentage of O over 18. Shit, hold on. Is it over 6 or is it over it's over 12, duh, because molar mass. Yeah. And then you get the ratio, and then you can basically derive the empirical formula from that. Molecular formula, you add an N before it, and you know the whole molar mass of the molecule at the end, and then you just do some dividing, and then some, there we go, N. Combustion analysis, again, this is like, the syllabus is just all over the place. Combustion is supposed to be way later. It's supposed to be like the first thing in organic chemistry. Well, it can also be a little bit before, I don't know. Chemical equations, stoichiometry, mass stoichiometry, so, you know, number of moles. I love my Wi-Fi, hold on. I'm gonna grab a piece of candy because that is probably my only source
Hello, folks, and welcome back.
Stop it. Organic chemistry. Well, stoichiometry, so, you know, number of moles. I love my Wi-Fi. All right. Hello? Is it working now? This is a butterscotch candy, and it's supposed to have about 65 calories. So watch me consume these calories, babies. All right. Ionic equations, polar covalent solutes. Water and oil don't mix. That's why. Water is polar. Oil, you know, lipids. They're usually non-polar, so they don't mix. Simple as that. Strong, weak, and non-electrolytes. So strong electrolytes completely dissociate. And strong electrolytes include strong acids, strong bases, and soluble ionic compounds. If it is soluble in the ionic equation, it must be separated. Yes. All right. All right. Non-electrolytes do not dissociate at all. It does dissolve, but it doesn't dissociate, which are two different things. You know, they're different. All right. Non-electrolytes do not dissociate at all. It does dissolve, but it doesn't dissociate, which are two different. Electrolytes do not dissociate. Electrolytes do not dissociate at all. It does dissolve, but it doesn't dissociate, which are two different things. You know, they're different. All right. Non-electrolytes do not dissociate at all. It does dissolve, but it doesn't dissociate. Oh, the Wi-Fi is so bad. Everything in LA, man. I know this is about chemistry, but oh my god. Oh my god. Okay, I don't care. The OBS and the YouTube has already disconnected like 12 times already. More like 5. Dilution equation is MV equals MV, so that is obviously molarity times volume. So, you know, 0.5 m times you know, 500 milliliters, aka 0.5 L, yada yada. Concentration of specific ions in an ionic solution times number of moles of that ion in 1 mole of that compound. What the hell did I write? Concentration. I think what I wrote here is like a specific type of problem. Okay, so concentration of specific ions in an ionic solution. So like concentration of salt in a salt solution, so number of moles of that salt in 1 mole. Oh, okay. So what did I write here? I don't know. I don't know what did I write here. It doesn't make any sense. But it's fine. It's going to be easy anyways. Double displacement reactions, AB plus CD equals to AD plus CB. Precipitate is formed, water is formed, gas is formed, the solubility chart. So this is going to be fun because I would have to remember what is soluble and what is not. Neutralization reactions. Okay, I'm going to add a star here. I'm gonna highlight this with green so that I know I'll come back to this. Neutralization reactions, gas forming equations, complete and net ionic equations, redox reactions. It's so stupid. Redox reactions are literally the worst part of the chemistry world. But what this course does is that it briefly mentions redox reactions and then completely ditch it. When in fact you can spend weeks on redox reactions alone. The oxidation numbers, the chemical cells, the electrolyte cells, I forgot, but you know, the anodization, its applications, everything. It's so complicated. Solution stoichiometry, equations involving number of moles, volume, mass. Okay. Chapter 5. Okay, this is where the chemistry course borders on physics. Actually, this is literally physics. Gas properties and pressure, so properties of gas. STP is standard temperature and pressure, so 0 degrees Celsius and 1 atmosphere. Not room temperature. I always had the misconception that STP is room temperature and 1 atmosphere. No, it's 0 degrees Celsius. Not 0 Kelvin, it's 0 Celsius. Don't know why. aka 273.15 Kelvin. Yeah. Kinetic molecular theory, there's the pressure equals force over area, there's units of pressure, you know, torr something, TORR, I forgot. Atmosphere, there's millimeters of mercury, mmHg. That's my favorite one. It's so whack. Alright, simple gas laws. So Boyle's law is PV equals PV. Charles' law is T over V equals T over V. Avogadro's law is V over N equals V over N. Gay-Lussac's law is P over T equals P over T. Simple. So P is pressure, V is volume, T is temperature, and the small n is the number of molecules. I don't think it's the number of moles. Well, it's the same. Oh, n is the number of moles. Number of moles times 6.023 times 10 to the power of 23, I believe, is the Avogadro's number, which is denoted by n with a small a underneath. that is the number of molecules. Or just the number of whatever there is. A lot of people think number of moles is a legit number, but that is where you're wrong. Number of moles is just a number. It's not actually a unit. It's not an amount. So number of moles and amount are two different things. Like, if you have number of moles is a legit number, but that is where you're wrong. Number of moles is just a number. It's not actually a unit. It's not an amount. So number of moles and amount are two different things. Like, okay, the latency is just so strong. All right, we could go. Disconnected 7 times. All right. Ideal gas law and molar volume. So PV equals nRT. Everybody knows this. And because n is number of moles, and number of moles is mass over molar mass, you can derive a new equation. P times molar mass equals a dRT. And also R is 8.31. That's a gas constant. But in America, for some fucking reason, it's 0.08206. You know why? Because they decided to use liters, I think, which is the reason why. I don't know, but it's 8.31. The standard one is 8.31, but America likes to be different. Molar volume is 22.41 liters per moles. And this is so good. I love molar volume because it has disconnected for 8 times. It has disconnected for 8 times now. All right. Okay, so this is the first thing that I actually have not learned so far in my life. Finally, something challenging in chemistry. Yes, finally. You're doing it. So, in gas mixture, the partial pressure of each gas is proportional to its number of moles. So in a mixture of gas, different gases actually have different pressures. It's not like all one pressure, you know. And according to Dalton's law, all partial pressures add up to total pressure. And total pressure is just, you know, total pressure. RT over V times number of mole of gas, which is derived from PV equals nRT. Wi-Fi so bad. Liter, and total pressure is just, you know, total pressure. RT over V times number of mole of gas, which is derived from PV equals nRT. Wi-Fi so bad. Liter, and total pressure is just, you know, total pressure. RT over V times number of... Alright, it's the 9th time this has happened. I will keep count of that, because fuck this Wi-Fi, okay? No matter where I go, okay? Back in Hong Kong, I thought, okay, maybe when I go to LA, the Wi-Fi is going to be better. No, every single settlement I've been to, the Wi-Fi is shit. Alright. Diffusion and effusion of gases. URMS is root mean squared velocity of gas particles. In room temperature, it can be 100 to 1,000 meters per second. Diffusion goes from high concentration to low concentration, 1 to 10 feet per minute. We all know that. MFP is mean free path, and it is the average distance a particle can travel between collisions. And when the pressure is lower, mean free path goes up. So we all know that. MFP is mean free path, and it is the average distance a particle can travel between collisions. And when the pressure is lower, mean free path goes up. So we all know that. MFP is mean free path, and it is the average distance a particle can travel between collisions. Okay, great. So my stream has died 10 times already. Exactly 10 times. Because the Wi-Fi in Los Angeles is absolute fucking garbage. So it's literally going King Crimson on me. It's like I'm skipping time. I'm literally time traveling because the Wi-Fi of Los Angeles is so goddamn bad. Ugh. It's been 10 times. Alright. The 11th time. Let's go. So, effusion rate of gas A over B equals the square root of molar mass of B over A. Remember the excess. Okay. I need to highlight this actually, because I always mess this up. And by fuck, I can't even use my fucking mouse because it's so bad it's breaking. Everything's breaking on me. I don't know why, but okay, so if I try to, okay, it's done that already. Energy does not either does work or is converted into heat. The system is a thing we're focusing on, and the surroundings is anything that is not the system. Okay, so Q is heat, W is work, triangle is delta, and delta is change, so change of energy is Q plus W. Now remember this basic equation. Now we have the difference between endothermic and exothermic, and we all know what does that mean. Endothermic is absorb heat, exothermic is release heat. W is negative P times delta V. Negative P is pressure in liters. What? In atmosphere. And V is a liter. Which means that if gas expands and the pressure also goes up, or I guess depending on how much pressure change there is, there's work done. And it also equals to delta nRT. So PV equals nRT. Literally. Yes. If the gas expands, work done, work is done by the system. So it goes outwards. So it's W minus. If gas contracts, it's work done on the system. So work done by the system. So this is the system, right? This is the cup, this is the system, okay? When the gas expands, work is done by the system to the environment. If the gas contracts, the work is done on the system, so it goes inwards, okay? Fuck me. Total number of moles of gas remain unchanged. W remains 0. That's a W. Oh, it just died again. Frozen 3 starting in the middle. I hate Los Angeles. It's Los Angeles' fault. I'm literally going insane studying chemistry. Oh, it just died again. Frozen 3 starting in the middle. I hate Los Angeles. Okay, my OBS seems fine now, so okay. Delta H in chemical reactions. Yay! Enthalpy is H, energy is E. So let's do an equation or formula. H equals to E plus PV. Okay. So under this only works under the condition of constant pressure. Now this means delta H equals to delta E plus P delta V. So everything's changing, but the pressure, because the pressure is constant. But energy doesn't change naturally, does it? Turns out the enthalpy change is the change in energy due to P delta V, which means that energy isn't actually changing naturally by itself. It's changing because there's work done, man. I mean, there's work done. Like something's cooking up in the system. Okay, it's heating up. It's getting hot. And then, like, the gas expands. Boom. Delta E equals to Q plus W. Delta E equals to Q minus P delta V because of that. Again, Q plus W. Heat and work done. Makes sense. Thus, delta H. Okay. W equals to negative P times delta V. Okay. Thus, delta H equals to delta E plus P delta V equals to Q minus P delta V plus P delta V equals to Q, which means that delta H is Q. So enthalpy change is just heat. Heat, enthalpy change, same thing. What? The catch is it only happens under constant pressure. Okay? Which means that, you know, constant pressure, 1 atmosphere inside the cup, 1 atmosphere outside the cup. Why? Because there's no lid. 1 atmosphere, 1 here, boom. So, oh my god, it's heating up. Oh my god, So, I just sent 100 kilojoules into this cup of water. So the enthalpy change, guess what? 100 kilojoules. Okay. When the gas expands, delta V goes up slightly, and delta H is slightly greater than delta E. So chemical potential energy goes down when heat is released, so negative QP, so negative delta H, exothermic. What am I even? I don't think it's negative QP. I think it's just negative Q. What the fuck's happening? So negative QP, so negative delta H, exothermic. I don't know what the fuck is happening. Okay. What am I even? I don't think it's negative QP. I think it's just negative. What the fuck's happening? All right. So why? Because when heat is released, Q is gone. Negative Q, baby. Negative Q. That's right. Negative Q, negative delta H. Only if it's constant pressure. Okay, when gas expands, volume goes up slightly. Blah, 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 blah. Okay. I think I can get the hang of it. Thermochemical equations. That's a balanced equation that includes a delta H at the end. So delta H, enthalpy change is an extensive quality. So it really depends on the amount of material reacting. For example, for every 2 moles of strontium hydroxide to decompose, it absorbs 300 kilojoules. So for every 0.02 moles, it absorbs 3 kilojoules. Enthalpy change in Hess's law. Oh my god, I love Hess's law. Oh my god, Hess's law so hot. Oh my god. Yeah, Hess's law is basically you know, going from A to B is the same thing as going from A to C to B. There's no difference at all. That's Hess's law. So if H2O becomes, okay, that's a bad idea. That's a bad example. I don't know how to explain it now, but you know the drill. Using the coefficient multiply and reverse moves to calculate the delta H. So in Hong Kong, what we do is we literally draw Hess's law. We literally draw a triangle. We literally draw a whole map. A to B, A to C, C to B. So, you know, this and this, it all makes sense. But in America, we do it the rough way. We literally list out all the equations, and then we flip it, multiply it, and somehow it works better in an American exam. All right, heat transfer and calorimetry. So Q, oh man, one of my favorite equations of all times. Q equals mc delta T. In an exothermic reaction, Q is negative because, hey, you release. But the solution is positive because surrounding solution gains heat. So bomb calorimetry. So in a bomb calorimeter, Q equals to C delta T. C is the specific heat capacity of the entire calorimeter, delta T is the temperature change, and Q is the heat. That is constant volume, which means that there is a lid, which means it's a bomb for some reason. So the volume remains constant, which means the energy change is the heat release, because there is no work done. Gas does not expand, nothing happens other than the thing heating up. So the thing heating up is literally all the energy there is. It's just heat. No work is done. No work, bye-bye. But in a constant pressure calorimeter, like a coffee cup calorimeter, where it doesn't have a lid, it's open air, you know, then enthalpy change is heat. Hold on. I don't 100% know what I'm saying here. Because there's no pressure or volume change. And pressure and volume is the work of work done. So bad. Where was I? Calorimetry calculations. And pressure and volume is the work of work done. Alright. Calorimetry calculations. A thing mixed with another thing is a heat loss of one thing equals the heat gain of another thing. Easy. So, hot ball of metal dropped into a cold water. The cold water heats up. The hot ball cools down. How to use Q to find delta H. My notes are so vague. I should have written something else, really. Alright. So HCl plus NaOH equals to H2O plus NaCl. Classic neutralization. In this reaction, 0.05 moles of hydrochloric acid is reacted to release 2 kilojoules. So 0.05 over 1 equals to 2 over x, because we need to know how much energy is released in 1 mole when 1 mole of hydrochloric acid reacts. Yes, remember to do the positive negative flip between reaction of Q and reaction heat of reaction and heat of solution. Yes. Standard enthalpy of formation. So standard enthalpy is delta H with a degree. Delta HF degree is standard enthalpy of formation. So there are values that occur at standard state. Standard state is 1 atmosphere and 25 degrees Celsius. That is not STP, that's standard state. Standard state of solution is 1 molarity? I guess so. And yeah. Chapter 7. Okay, this is where it starts to get really so there are values that occur at standard state. Standard state is 1 atmosphere and 25 degrees Celsius. That is not STP, that's standard state. Standard state of solution is 1 molarity? I guess so. And so there are values that occur. Alright. Bohr model. This is where it starts to get juicy as fuck. Okay. So Electromagnetic radiation, FBI, left hand, so left hand. FBI, right? This is force. This is magnetic field, and I is the current. So if I goes from here to here and the force goes to, it's physics. Wavelength is in lambda and it's in meters. We have altitude. Frequency, it's nu and it's 1/2. V equals F lambda, so C equals nu lambda. Because C is the speed of light. So V equals F lambda is an equation that works for every single wave to ever exist. So it could be sound waves, it could be just waves of water ripples, just waves in general, really. But this is specific to electromagnetic waves, like, normal light rays, infrared, ultraviolet, gamma rays, whatever, X-ray, you name it. Radio waves as well. And it's C equals nu lambda because C is the speed of light, aka the fastest possible speed of anything ever. And C remains constant, but the frequency and the wavelength, they're different. So we have the electromagnetic spectrum with the black body radiation, which is a metal. When it gets heated, it gets so hot it glows. And it glows in different temperatures depending on it glows in different colors depending on what sort of temperature. So we have the Planck's equation, delta E equals NH nu. The nu is frequency, H is 6.626 times 10 to the negative 34. N is the atomic number, not number of moles. No. It's atomic number. And it's the atomic number of the metal. And negative delta E is the energy change of the system. And their photoelectric effect. E photon equals to H nu, thus E photon equals to Hc over lambda. Easy. So H and C are both constants, right? So E photon is the energy of the photon, really. All right. So photoelectric effect. When light shines on a metal that are certain frequency or higher, and that threshold is nu naught, electrons are rejected. The kinetic energy of the ejected electrons also increase as the frequency of the light wave increases as soon as it's higher than nu naught. Albert Einstein found out about this. Quick shout out to Albert Einstein. Electrons are bound to protons with binding energy, E naught. If E photon, energy added to the metal, is higher than E naught, well, guess what? Okay, so how do I illustrate this? There's a piece of metal, and the metal is full of atoms, metallic atoms, metallic elements, and a light shines. It hits. And if this frequency of the light wave, if it's high enough, an electron will be ejected. And to do that, they have to overcome the binding energy, which is E naught. So E photon, which is the energy of this thing, has to be higher than E naught. Thus, the kinetic energy of the ejected electron is E photon minus E naught. Thus, it is H nu or minus E naught. Thus, it is Hc over lambda over E naught. Not Enoch, not my name. All right. Okay, here's the fun part. Bohr model. So each orbit is a shell, an energy cell. Okay, so right now we're borderline talking about physics, but also chemistry, but also physics, And I'm gonna grab a piece of food. Jelly. I'm gonna eat some jelly. Hold on. Konjaku jelly. Well, let me just grab that real quick. 1 sec. Tadaima! Minna gome ne. Tadaima! There we go. Alright. So, this is an atom, okay? In the middle, we have a bunch of neutrons, which are neutral, and protons, which are plus, positively charged. And we have a bunch of electrons going around it. Zoom, 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 zoom. Now, as you all know, if you have studied chemistry at all, these electrons don't just circle around it. They got layers. They got levels. See, there's level 1, n equals 1, aka E equals 0. And then n equals 2, which means E equals 1. N equals 3 means E equals 2. And as we all know, is 2, 8, something, something, something. So 2, 8, 18. Even though we're always, like, we always draw it like 2, 8, 8, 2, but 2, 8, 8 something, but it's 2, 8, 18, and so on and so forth. The further away from the nucleus, the n level is higher, and the potential energy is also higher. So now we have the Bohr equation. En is the potential energy of that level in joules. N is the energy level as a whole number. Z is the nuclear charge, aka number of protons, aka atomic number. So, you know, hydrogen is a 1. Helium is a 2. Yes. Not 4. Not 4. No, no, no. Not molar mass. 2. And R is a Rydberg constant, which is 2.18 times 10 to the negative 18 joules. This equation only works for one electron system. Wow, what a cool equation. Psych! It only works for one electron system. So if the system has one electron, it works. If it has more, you're screwed. So, you know, anything from hydrogen atoms to helium plus to lithium 2 plus to beryllium 3 plus to boron 4 plus, which is just stupid, but you know. When an electromagnetic radiation excites an atom, the electron jumps to a higher energy level. So this is the electron, okay? This thing, it's the electron, okay? A light comes in, wow, it jumps, it gets excited, holy shit. So it jumps from level 1 to level 2, or maybe 1 to 3, or maybe 1 to 4, or maybe 2 to 3, or maybe 2 to 4. It just jumps. It gains energy. And then it'll go back down to n equals 1, or maybe whatever. Just go back down. Energy is released. When it is released in photon. It is a light. So energy of the photon release is literally the energy change, regardless of so the absolute value of the energy change, essentially. Now, if you use a Bohr equation, you will know that the energy level of E1 or so E1 is basically the potential energy of level 1. E2 is the potential energy of level 2, so on and so forth. So if I jump from 1 to 6, then calculate how much PE there is in 1, how much PE there is at 6, calculate the change from 1 to 6, and then absolute that value, and then you get the energy of the photon. And then when you have the energy of the photon, use E photon equals to h nu to find the frequency. H is the constant, Planck's constant, easy peasy. Nu is the frequency. Boom. All right. Okay, what if the electron jumps so high it straight up flies off? What if that happens? N equals infinity. How about that? Well then, sir, unfortunately I have to tell you, the atom has been ionized. It turns into an ion. The electron, it just flew off. Bye-bye. Good day. Electron, basically gone. How do we calculate that? We calculate the ionization energy. The ionization energy is the energy required to ionize the item. To calculate that, we calculate the energy change of E infinity minus E initial. And E infinity is literally 0. So 0 minus E initial, so literally negative RZ square over N square. So minus minus is plus, so ionization energy equals RZ square over N square. Simple as that. Alright, the radiation emitted by excited atoms or ions are passed through a prism to reveal colors. Oh my god. And different excited atoms show different color patterns. Different transitions result in different colors. For instance, if N4 to N1 is purple, N3, N2, N1 is blue, N3 to N1 is green, etc. Who cares? Okay, developing the quantum mechanical model. Here we go. Now, Bohr model isn't perfect because it only applies to one electron systems. But let's talk about Louis de Broglie. So if an EM radiation can simultaneously be particles and waves, can matter be like that too? Introducing lambda equals to H over mv. So lambda is a de Broglie wavelength. It's like a wavelength, but not really. I mean, how do I define the exact wavelength of me? Let's say this, my finger. What's the wavelength of my finger right now? I don't know. To me, it doesn't seem like it's moving like a wave. To me, it's just a particle. My finger, my skin cell, the phospholipid molecule, the phosphorus atom in my phospholipid molecule, in my cell membrane, in my skin cell. It's a thing. But what if it's moving like a wave? Well, we don't know, so we have to make up a new thing called the Broglie wavelength. All right. M is particle mass, and it's in kg for some reason. V is velocity. H is Planck's constant. Now, this means if the mass is higher, the wavelength is lower. If the velocity is higher, the wavelength is also lower. So, now instead of envisioning my finger, envision a ball, envision a football. So if it is a big football, the wavelength is lower. It's so low, you don't even see it moving. But if it's as small as an atom, ooh, maybe it is. So diffraction patterns observed when X-rays pass through aluminum foil. De Broglie thinks the electron acts like a standing wave. This means that electron wavelengths must be whole numbers, otherwise there will be destructive interference. Yeah, so, you know, if the wavelength is friggin' 0.5, then it's just going to act weird, I guess. I want to wash my hands. Hold on. And then I'm going to talk about the Heisenberg uncertainty principle. Okay, let's go one step further. Shit. With this principle, we can know the exact position and speed of a particle at any time. Insane, am I right? I know. So this is the formula. Delta X times M times delta V is at least H over 4 pi. So H over 4 pi, H is Planck's constant, 4 is a constant, come on, pi is a constant. So H over 4 pi is kind of like a circumference around the H, or more like H times the circumference of something, or the inverse of a circumference, without the r, without the radius. I don't know how is this thing derived. Leave me alone. Delta x is the uncertainty of the particle's position, and delta v is the uncertainty of particle's velocity. M is the particle mass. This is my favorite part of the whole course. This is my favorite part because it's so abstract, and I love that shit. This equation means that the uncertainty of position and velocity can never be zero because it's always at least 4h over 4 pi. So this literally means, this whole formula literally means that we will never be sure where the particle is and how fast it's going. We will never ever be sure in ever. Now, but what this formula also says is that delta x and delta v are inversely proportional. So the more certain you are of the position, the less certain you are of the velocity. Remember, delta x is not position. Delta x is the uncertainty of the particle's position. This means that, oh, the particle's right here, but I have no idea how fast it's going. Oh, the particle's going this fast. I have no idea where it is. And another thing is, the smaller the mass, the more uncertain you are of the position and the velocity. It's so small, I have no idea. This means the velocity of the particle relates to its wave nature, and the position of an electron relates it to particle nature. This means particle-like and wave-like are complementary natures. So if you're more certain about the position of that electron or that particle, then it's more like a particle. If you're more certain of the velocity of that particle or that electron, then it's a wave. There's a Schrödinger's equation. H naught psi equals to E psi. So psi is a wave function of the electron. So a function like f of x equals to f of x equals to mx plus c. So f of 2 equals to m2 plus c. Okay, and that mx plus c, that is a straight line, of course. And then there's the parabola, there's the the cubic equation, and there's whatever. But at some point it gets so complicated that there's a wave function where you basically see the x, y, and z coordinates of the electron. So you know how the electron moves in all 3 dimensions. Oh yeah, it's going here and there and here and there. That is the wave function. H naught is the Hamiltonian operator, which is a series of mathematical instructions, which I have no idea what it's about. E is the energy of the electron. So these wave functions are basically atomic orbitals. And this basically means the energy of the electron, I don't even know what it means, but what I know is that psi squared becomes probability density, which is the probability of finding an electron in a region of space. And the closer the electron is to the nucleus, the higher the probability density. All right. Something weird is going on. All right. All right, let's continue. Orbitals and quantum numbers. So this is where it starts to get fun. Different electrons have different wave functions, thus different orbitals. So take quantum number n. n is related to the size of orbitals. The higher the n, the farther it is the electron to the nucleus. So n can be 1 to infinity. So like I said, n equals 1, 2, 3, 4, 5, blah, 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 blah. Okay, angular momentum quantum number is L. So it is related to the shape of the orbital. So L can be 0 to infinity, but it's always less than n. So this means if n equals 5, L can be 1, 2, 3, and 4. And when L is 0, it's S. When L is 1, it's P, and then D, F, G, and H, I, J, K, L, M, N, O, Q, R, T, U, V, W, X, Y, Z, A, B. I don't know. Orbits that have the same n level and L level, they are occupying the same subshell. Doesn't make any sense. Occupying the same n level and L level. So L is sublevel. So n is the quantum state. L is the sublevel. S is the subshell. Each okay, I have to visualize this, but first level is n equals 1. And inside n equals 1, you can have L plus 0. And then inside L plus 0, you have 1s. And s is 1 orbital. And each orbital has 2 electrons. Yeah. So n equals 2 has 2 sublevels. N equals 0 and n equals 1, and it's 2s and 2p. 2 is the quantum state, and then s and p. S can hold 1 orbital, p can hold 3, d can hold 5, f can hold 7. So this means n equals 1, you get 1, n equals 2, you get 4, n equals 3, you get 9, n equals 4, you get 16, so on and so forth. You see the pattern. So n equals 5, 25, 36, 49, 64, etc., etc., etc. So the magnetic quantum number is m subscript L, and is related to the orientation of the orbital in relation to other orbitals. So it has to be whole numbers, and it has to be negative L, 0, negative plus L. So so if L equals 1, the p orbital, this means there are the p subshell. This means there are 3 orbitals. So it's negative 1, 0, plus 1. And each orbital has 2 electrons, and it can go up spin or down spin. It's arbitrary, really, so it's not real up and down. It's more like they're just opposite of each other. And ms is either plus half or negative half. Different spins have different magnetic poles, so, you know, there's that. For example, 2p means 2 as in n equals 2, second level. P means 3 orbitals. So 3 times 2 is 6 electrons. Now we have the orbital shapes. S is just a circle, P is a double lobe, D is 4 lobe, F is just whack. Alright. Pauli exclusion principle. So N, L, ML, and MS can never be the same 4 numbers. This means an orbital can only have 2 electrons since there are only 2 MS values and they can't be repeated. Thus, when n equals 2, there is up down to S and up down to P. Oh, I see. I get it now. Alright. Ouch. So this is why there can only be an up and down. Because there are only 2 MS values. Alright, filling electrons. So electron configurations and orbital diagrams. Orbitals and atoms are filled according to potential energy. So we got an atom, we got a proton, we got protons and neutrons. Nice. Where are the electrons? Gotta fill them up, man. We gotta fill them up. So in a one electron system, if the n level of the electron is the same, the potential energy is the same. So okay, yeah. So in a one electron system, it's just one n level, I guess. Or not really one n level, but more like there's just one electron. So, you know, potential energy, the electron in n1, electron in n6 is the same. But in a poly-electron system, it doesn't work like that. As n and l go up, the p also goes up. The p level is proportional to n plus l. Alright, so this means 1s, 2s, 2p, 3s, pd, 4s, pdf, etc., etc. The p levels are not in order. So you can't fill in like, okay, let me just fill up the electrons, you know, 1s, 2s, 2p, 3 SPD, 4 SPDF, blah, blah, blah. No, it doesn't work like that, because lo and behold, 4s actually has a lower PE than 3D, even though 4s is like above, like it's n equals 4, it's above. But no, we gotta fill 4s first, and then we go back down to fill 3D. So the best way to do it is to literally do a table and just do it diagonally. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, so on and so on. Electron configuration shows the number of electrons in each subshell. So sodium is 281, because sodium is number 11, right? So 2 plus 8 plus 1, easy. Okay, let's divide it. 281 is the 3 levels. So 2, the first level is 1s, so 1s2. 8 can be divided into s and p, because 8 is in level 2. So 2 plus 6, perfect. And then next one is 3s1. And then with the orbital diagram, where it goes even harder, where you show the up and down spins. So 1s, 2s, 2p, 3s. This is getting super freaking boring. I'm trying my best to study here, man. Abbreviated notion, aka noble gas notations, replace a part of the electron configuration or orbital diagram with a noble gas in the square bracket. So, you know, 1s2, 2s2, 2p6, come on. Nobody's going to write all that. So let's just replace a chunk of it with neon. Yay! Hund's rule. Place an electron of the same spin in each subshell evenly. So in oxygen, it's like 1s2, 2s2, 2p4, because 2 plus 2 plus 4, that's 8. That's oxygen. But we fill it like we fill up evenly. So we don't like do it at one side. We try to do it. So for 4p, there are 3 orbitals. So 1, 2, 3. So px, py, pz. So electron here, electron here, electron here. Instead of just stuffing all the electrons on one orbital. You know, it doesn't work like that. You need to spread it out evenly. Alright, there are many transition metals and intertransition metals that do not follow the general filling rule: chromium, copper, molybdenum, and silver. So here's what they are. And then we have the absolutely amazing periodic table. That basically is a whole cheat sheet. You know, 3D, that's the 4D side, 5D side. And that's basically what's the last chunk in that electronic configuration. That's good. So 3D, you know, gallium and germanium are in that section. And I know the electronic configuration of gallium and germanium, it ends with 3D something. 3D 1? No, 3D something. I don't know. I know it. I think it's 3D1. Is it 3D1? Gallium electron configuration. It's 3D10. Haha. But yeah. And it is it's following the wait, what? It's 4p? Oh, gallium is all the way over here. Alright. Shit. Scandium, titanium. Okay, I get it now. If you only see the last bit of blah 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 blah, diamagnetic atoms, all electrons are paired. Paramagnetic atoms, unpaired is magnetic. Blah blah. Valence electrons, they're outermost shell electrons. All valence electrons are the highest end level. Okay, so Lewis dot structures. Valence electrons can be identified by measuring the successive ionic energies of each atom. So how much energy to remove an electron from an atom? So there's A. Pluck one electron out, you need a lot of energy. Pluck another one out, you need a little bit less. Or you need a little bit more. Pluck another out, you need even more. It requires more and more energy. So why is it that in a carbon atom, the ionization energy for 1, 2, 3, 4 is slow, but suddenly 5, 6 goes super high? Because 5, 6 are n plus n equals 1. So 5, 6, so it actually goes 1, 2, 3, 4. Okay, that's outer n equals 2. And then 5, 6. You need so much more energy because you're a whole level closer to the nucleus. Periodic trends. So atomic radius, across a period, radius decreases. Down a group, the radius increases. Across a period, the IE1 increases. Down a group, the IE1 decreases. So IE is the energy required to remove the first outermost valence electron. God, I'm so bored by my own talking. It's fuck. I'm gonna take a break and cut myself an apple or something, maybe. You know, after this, and then, yeah, after chapter 7. IE1 is the energy required to move the first outermost valence electron. So, yeah, across a group, IE1 increases, down a group, IE1 decreases, so if the atom is bigger, you actually need less energy to just pluck it out. True that. But across a period, IE1 also increase because number of valence electrons increase. So it's like, yo, we don't want to lose you. Effective nuclear charge is Z star. It's the attraction between the outermost shell electrons and the nucleus. Z star is higher when the n level is lower. Z star is higher when shielding effective core electrons are less. Core electrons block the valence electrons from experiencing, you know. So, you know, Z is number of protons in the nucleus, and then S is number of core electrons. So core electrons are anything but valence electrons. All the electrons but valence electrons. So if it has too many core electrons, it just shields, man. It acts like a cloud. Nucleus, like, come on, electron, get close to me. But then the core electron literally blocks it. Just like a cloud. Higher Z star means radius lower, IE1 higher. Down a group, the Z star decreases. Okay, but why is the slope from L1 to lithium, from lithium to neon so jagged? Also, you know, what are all these variations? What are all these dips? Why are these lines so squiggly? I mean, it should be a smooth line, right? It should be a smooth line. You know, lithium, easy. Ionization energy, blah, gone. Why? Well, because it's just 2 plus 1. So just take one out, plop, you're good. But for something like a, noble gas, you know, neon, argon, krypton, xenon, 8 electrons at the outside, full army. Plucking one out is going to be so much more difficult. But there are still these variations. It's not a straight smooth line. Why? Because we got these filled subshells and half-filled subshells that are, for some reason, a little bit more stable. Okay, I'm gonna go cut myself an apple, take a break. Yay. Can I pause the stream? I just wanna like check my... Anyone up for some small talk? At least this is easier than Hong Kong chemistry. I need to take a mental break. Should I play some background music? I feel like I should. Let's find some music that is like not copyrighted. Where is it? Wait, hold on. Is it working? I can't play Death Grips, it's copyrighted. I can't do it. I can play this though. Oh, it's so good. Like the soundtrack to Kizumonogatari, it's just amazing, really. It's just fantastic. What can I say? Composition, the style, and just how whimsical it is, the attitude. Exquisite soundtrack. Rate this track 10 out of 10. What can I say? Awesome soundtrack. Let's eat some apples, guys. Ooh, apples. The carbohydrates, the fructose. Wow, the fructose is reacting. It's being oxidized, or the flesh of the fruit is being oxidized. Oh wow, redox reaction. It's happening right in front of our eyes. Chemistry moment. Mr. Morale could never. Kendrick gotta up his game. Alright. Chapter 8, Bonding. I mean, come on. Who doesn't love some bonding? I do some bonding, you do some bonding, he do some bonding, she do some bonding, we all bonding. But this time we're talking about molecules. That's a little different. So ionic formation and ionic bonding. So atoms bond to lower their potential energy and become more stable. Noble gas, no bonds. Monoatomic anions always have a larger radius than the original atom, smaller radius if cation. Formation of Okay, so NaCl, man, the classic. NaCl, sodium and chloride. Sodium chloride, that's salt. That's table salt. Sodium is 281. Chloride is 287. It's 287? Yeah, it is. So 281, 287. I mean, what can I say? It's a match made in heaven. I mean, the Na, the sodium, can just give one electron to the 287, so now it's 28 and 288. The octet rule, it's perfect. It's a match made in heaven. And voila, everybody happy. Now, it gets a little complicated because some main group metals can form two stable cations, like tin can form tin 2 and tin 4, and indium and thallium and tin, lead, bismuth, they can all form whatever crazy ions. They only lose their electrons in their p subshell, or they lose both s and p subshell electrons. And then we got the transition metal cations that can form multiple stable cations. The first stable cation is all the s electrons. Bye-bye, all gone. Now keep in mind, s and p, that's the valence, man. That's the valence electrons. S and p. S, p, p, p. So 1, 2, 1, 2, 1, 2, 1, 2. That's 8. So that's the outer shell. They can go. I'ma go wash my hands. And I'm back. Where were we? Right. So lose all the s electrons, but instead of starting to lose the p electrons, it starts to lose one or more d electrons, just one by one, except for silver. Because silver is a 5s14d10 at the end. So if you take one out, it becomes 5s14d10. Five S149. Okay, I fucked up. Did I? Okay. 5s149. Let's talk about ionic compounds, right? NaCl. A grain of salt. A grain of salt isn't just NaCl. A grain of salt is NaCl, 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 blah, 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 all connected into one big clusterfuck. Cation, anion, cation, anion. And the repeating unit, NaCl, is a formula unit. Now we have lattice energy, and lattice energy is formed when a lot of ionic compounds together to form as a crystal, like one grain of salt. And they're attracted by electrostatic or Coulombic attraction. So x plus y equals to xy. So this formation, the energy released, is the lattice energy. Yes, it releases energy. Releases energy when it forms bonds and absorbs energy when it breaks bonds. Higher lattice energy means it's more stable and has stronger ionic bonds. Lattice energy is proportional to Q1, Q2 over D. Q1, Q2 are the charges of the ions, cation and anion. Remember, charges of the ions, so not the small number. So NaCl is 1 times 1 because it's literally 1 to 1. But if you do something like magnesium aluminum oxide, so literally aluminum 3 minus, or okay, that's a bad magnesium oxide, MgO. It's like 1 to 1, right? Wrong, it's 2 to 2 because it's Mg2 plus O2 minus. Okay. D is the internuclear distance between adjacent ions. So, okay. So, higher lattice energy means higher melting point and it's less soluble. Principles of covalent bonding. Okay, this is when it goes crazy. Sharing pairs of valence electrons between 2 or more non-metal atoms. So, you know, we got 2 things here, man. 2 things. We got the carbon and we got the oxygen. So the oxygen is 2,6 and the carbon is 2,4. And so the carbon's like, man, I need 4 more. And the oxygen's like, man, I need 2 more. So what if we just slap together and share? Except now carbon needs another 2 more, so CO2. It makes sense. So a pair of valence electrons is a single bond. 2 pairs is a double bond. 3 pairs is a triple bond. Triple bond is the strongest, but also the shortest in bond length. Bond polarity, so electronegativity, it's a chi. Generally increases across a period and decreases down the group. So ON and S, I believe, or ONF, I believe, are the most polar, right? ONS, ONF, right? All right. So, okay, here's how you're going to draw a Lewis structure. Let's say, draw me NH3. That doesn't make any sense. Hold on. Okay, just okay, right. Draw me CH3F. Does that work? It works. CH3F. Ooh, okay. So lowest electronegativity here is obviously C. Start from H because we don't put H in the middle. So C in the middle, and then we do H, 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 F. Like a square. Not like a square, like a cross. But if you want to draw in perspective, you got to do C. Okay, C. H, 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 F. So it goes towards you and one goes backwards. And it's like a tripod with a thing on top. It's a tetrahedron. I am currently eating one of the most insane pieces of food in the world. Apples. To be specific, Fuji apples, purchased in the one and only Nijia market. Nijia. It's a little bit expensive, but... Oh, I actually didn't buy it there. I actually bought it at Ralph's. It's nice. I like it. Good apples. 80 something calories. That's good. I wish it's more. Alright. So, you know, all this talk about octet rules, you know, gotta have 8 at the valence. Some atoms are just like, fuck that. So now we have expanded octets and reduced octets. Some can still be stable with 10 or 12 valence electrons, and some can be stable with only 6. What the fuck? Well, in that case, we have to really use the method. Formal charge. So, the correct final Lewis structure can be confirmed with formal charge. Formal charge is the atom's original number of valence electrons minus number of valence electrons assigned. So, you know, like again, CO2. C has 4 outside. 4 valence electrons. C is carbon. But after we have CO2, well, I guess we have ourselves a couple double bonds. So all lone pairs of electrons and half of the bonded pair electrons. So 2 double bonds, so still 4. So 4 minus 4, it's 0. So that's cool. Sometimes it's not 0. Sometimes there's a +1, there's a -1. It happens. Shit happens. Sometimes there are 2 or more Lewis structures with the same formal charges. This means that they become resonant structures. So as you can see in my notes, oh my god, we have 3 kinds of CO3 2-, which is, by the way, the carboxide ion. No, wait. Carbonic ion. Carboxide. Oh, what? Is it carboxide? Oh, carbonate. I'm so stupid. It's carbonate. Why do we have 3 kinds? That's insane. Yes, that's true. We have 3 kinds. There are 3 ways to draw this. But what's really special is that there really aren't 3 kinds. If there are 3 kinds, then why not we call them, carbonate 1, carbonate 2, carbonate 3? No, because it's still the same. It's just that the double bond switches positions simultaneously at the same time. So it's not really 2 single bonds and 1 double bond. In actuality, it's 2/3 of a double bond. It's insane. I know it's insane. But FYI, this is how you draw a Lewis structure. So, NOCl, oh my god, panic. Okay, I guess N has are the least electronegative. What? Okay, electronegativity. List of elements in order of electronegativity. FOClN. Oh, F is even more than... Oh, okay, so FOClN. Krypton... Br is boron? Boron? No. Beryllium. No, beryllium is B. Shit. Bromine. Iodine, xenon. Okay, fuck. I'm so bad at this. I'm sorry. Sorry, folks. Sorry to let you all down. I'm a loser, I know. All right. N in the middle. So all the valence electrons, add them up, man. Add them up. Now, first of all, you got the bonds. Then you get rid of the O. Then you get rid of the Cl. O has 6 valence. CL has I'm back to that. You had an exam? What? Bruh. Everybody's having exams now. That's crazy. You good? Is it a good exam? Do you need help? Not so far, I guess. Hold on. Chlorine is group 7A, by the way. But it's 6 here. Because we assume it's 6. We don't care what's the valence of, like, we don't care. We just add 6. Who cares? Lucky number. Because we got the double, we got the single bond. Single bond is 2. 2 plus 6 is 8. Octet. Alright. We got 2 left. Where do I add them? At the end atom. Alright. In the resonance structures, one or more of the bonded pair of electrons are delocalized, superimposition, so resonance hybrid, covalent bonds, and enthalpy change. So covalent bond energy is a measure of how strong a covalent bond is the energy required to break that bond, also the energy released when the bond is formed. Obviously, triple bonds have higher CBE. You can actually use CBE to estimate enthalpy change of reactions. So, you know, enthalpy change is all the energy absorbed to break bonds plus all the energy released to form bonds. So that's good to know. VSEPR, valence shell electron pair repulsion theory. It predicts the shape of molecules. Steric number is the number of electron groups of a central atom. So, you know, CO2, I mean, 2. Yeah. Yeah, I'm in med school. I had medical English exam. Well, it went well. I got an A. I know chem. That is why I'm asking. Cool. Yes. Good for you. Getting an A. Let's go. It's still fine so far. Okay, VSEPR. Let's highlight this. Because I'm going to need to look at the table very soon. So there's a whole ass table of different molecular shapes, different geometries, all that stuff. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. You know, trigonal bipyramidal sounds scary, but really, if you think about it, it's just 2 pyramids. It's just one on top, one at the bottom. Okay, so use a steric number to get the electronic geometry, get the number of bond pairs and lone pairs, get molecular geometry. For instance, NOCl has a steric number of 3, right? Because N Right. 1, 2, 3, 4, 5, 6, 7, 8. Hold on. I'm starting to get confused. So I can draw two different Lewis structures here. Doesn't make any sense because N has a valence electron of 5. Why would it have two lone pairs and two single bonds when it only has 5? The best way to handle this is to have a double bond, either between Cl and N or N and O. And if you do the formal charges, you would realize that N and O double bond is the best. Now we have a steric number of 3. So it's trigonal planar, it's triangle. But because we know it's 2 bond pairs and 1 lone pair, it's not a perfect triangle. No. If it's a perfect triangle, it's 120, 120, 120. But now we have a lone pair. So now it's a little bit less than 120. So now it's a bent shape. Exactamente. What can I say? Oh my. Alright, I can do this, guys. I can do it. Alright, molecular polarity. So we all know this. Not the same as bond polarity. No. Nonpolar molecules have symmetrical shapes. Okay, so I need to know this as well. What shapes are polar, what are not? All polar bonds cancel out each other, no dipole moment. Okay, here we go. This is the craziest part of the whole course. The localized electron model, also known as the valence bond theory. So, for all our lives, we have been led to believe that it's 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. And when we fill electrons, we fill in a specific order. But when bonds are formed, fuck all that. Doesn't matter anymore. All these S and P and D and F, whatever, just mix them all up. Just mix them all up. I mean, answer me, right? C. Carbon is 2 plus 4, right? Because it's the first layer is 2 and then 4. So it's 1s2, 2s2, 2p2. How does it form 4 bonds if it's 2s2, 2p2? If it's 2p2, then there are 2 unpaired electrons and 1 empty orbital. So how does it form 4 bonds? Doesn't explain anything. It's because it doesn't even obey this SPDF thing. They all combine. So the LE model suggests that they're all combined, called hybridized orbitals. So again, with carbon, we got, so using the valence electrons. So 1s2 is going to be 1s2, but 2s2, 2p2 is forever going to be 2s2, 2p2. And we're going to have 4 orbitals where it's just 2s2, 2p2, 2s2, 2p2, 2s2, 2p2, 2s2, 2p2. Yeah, or just sp2. Yeah, or that. Duh. Hybridized orbitals with same potential energy are called degenerate orbitals. Hybrid orbitals still hold 2 electrons per, and so follow the Hun rules. Hybridization likely occurs in central atoms and atoms with double or triple bonds, but atoms with single bonds are less likely to be hybridized. The steric number can be used to predict the type of hybridization. So CO2, that's literally a steric number of 2. It's linear. SP, boom. 3 sp2, 4 sp3, 5 sp3d, 6 sp3d2. All right. Learning chemistry in English is completely different. I'm not used to it. Did you have any problem accommodating? Actually, when I learned chemistry in secondary school in Hong Kong, it's also in English, so it's not that difficult. The only thing that's really difficult, or not difficult, but annoying, are the units, because sometimes American chemistry uses feet, and I mean, it's not common, but sometimes they do that. Like, okay, feet, convert it to meters. And sometimes the constants are different, like R is always 8.31, the gas constant, but in America is 0.08206. So there's that. Some of the terms are different. Some of the calculation processes are different, I guess. Some of the methodology are different. Obviously, the Hong Kong methods are much quicker. Alright. Anyways, xenon diiodide. Crazy. Xenon is a noble gas, so the valence electron should be, S2p6. But it's still forming bonds. What the hell? Okay. Here's why. Its hybridization orbit is sp3d. So 5 orbitals. Steric number 5, 5 orbitals. And then there are 3 lone pairs, 2 unpaired. The 2 unpaired form 2 bonds. Boom, perfect. For molecules that involve double bonds, it gets complicated because there is partial hybridization. The C in CH2S can be hybridized into sp2 plus 1 extra pz. So that a double bond can be born in S atom. Born? I guess so. And again, head to head, side to side. So there's a little graph down there. So 2 orbitals crash into each other head to head. It's sigma. If it does a side by side, it's a pi bond, which is weak. Or in a triple bond, it's a sigma pi pi, And yeah. So I guess we can just check out this table. It's got unused p orbitals, thus forming double bonds and triple bonds, right? Used p form double and triple bonds. I'm literally doing research right now. Why do CC double bonds have sp2 hybridization and triple bonds have sp3? The electrons in s and p orbitals combine together to make a new type of orbital, a hybrid. If you have only single bond, you get sp3 hybridization because it's 1s and 3p orbitals. If you have a single pi bond, one of the p electrons is not used in hybridization, thus sp2. If you have 2 pi bonds, aka a triple bond, you have 2 p orbitals, so it's sp. Alright. I guess that makes sense. But again, N2 nitride. It's first of all, steric number is 2, SP, SPPP, because there are a couple unused. Thus, 3 unpaired electrons, 3 bonds, and it looks like this. All right. Oh my God. It's been 2 hours and 10 minutes. Why do you even have chemistry if you are in film school? America colleges work like that, so you have to take unrelated. Yes, so unfortunately, there's a thing in America called IGETC. Not everybody has to follow it. But if you plan to go to university or be in a university, in a public university in California, there's a thing called IGETC, where aside from film classes, you also have to take a bunch of other random classes, like chemistry or physics and biology. So I took chemistry, so I don't have to take physics. But I still have to take biology, though. And there's still a bunch more. Like math and English, that's compulsory. And in arts and humanities category, I already got film. But that's art. And yeah. I'm humanities. Spanish too actually is part of the humanities. So yeah, the feel when you're an unpaired electron. Pain, the suffering. It's not stopping. It's not stopping. The pain and suffering. I need an electron to pair me. This is what I'm gonna think about tomorrow when I do the final exam for chemistry and I see unpaired electron in the paper. I'm gonna be like. I'm gonna start sobbing, and the professor's gonna be like, "Why are you crying over unpaired electrons, dude?" My biology class, so in my college there are tons of biology courses. There's anatomy, there's a basic fundamental biology, there's genetics, there's a more advanced one for biology majors, there's the one dedicated to evolution. Me personally, I will take the fundamental biology class, which is going to be easy. That's good. Originally I planned to take the more advanced class because I wanted it to be more challenging, because of course everything in USA is easier, right? Especially in California, especially in a community college. Like, American college biology ain't got shit on Hong Kong biology. Like, I would argue that out of all the subjects in Hong Kong, biology and maybe math is the number one most advanced thing. Like, Hong Kong biology can, like, someone I know, Leo, who's a friend of mine, he well, he was a he back then, he decided to take Gaokao biology, which is the Chinese, the infamous Chinese exam, and he did pretty well. So, you know, just saying. But biology is probably more fun. I like biology more than chemistry. What uni are you trying to get into? UCLA, man. UCLA is my dream school. I want to get into film school in UCLA. So if I do get in, and you want to find me, just walk into the campus, and voila, I'm sitting there. There we go. My stream died again for some reason. I love my internet. All right. But yeah, aside from UCLA, there are a few unis I would like to go to as well. Like, you know, not go to as well, but in case I don't get to UCLA and USC, there are some backup plans like LMU and Chapman U, but both of them are very expensive, and I'm not that rich. In USA, you have to study in college first, and then you go to uni. Uni is more specialized then. That's not true. In USA, very expensive, and I'm not that rich. In USA, you have to study in college first, and then you go to uni. Uni is more specialized than. That's not true. In USA, very expensive. And okay, god damn it, my stream is dying. Okay, in USA it's 4 or 2 plus 2. So the normal path is 4. You do 4 years of university, and then that's it. You get the degree. Or you do 2 plus 2, so 2 years of college and then 2 years of university. In my country, I just went to med school straight from high school. May I ask which country are you from? Just, you know. In Hong Kong, after secondary school, you go to university first, and then I'm not 100% sure, but there's an extension. So university and then med school in Hong Kong. But I don't know, it's different in different countries, so there's that. All right, I need to return. Molecular. All right. Czech Republic. Nice. Hello to Czech Republic. I need to return. All right. Med school 6 years here. Yeah. Med school is also 6 years in Hong Kong. I don't know about USA, but yeah. All right. I want to go to Czech Republic. Like, that's probably one of my top 3 destinations in Europe right now. Like, if I get to pick any country in Europe to go to, Czech Republic would be in the top 3. And then I actually really want to go to Ukraine, but of course it's getting invaded right now. But the Balkan countries, they're just like very fascinating to me. Like, I want to go to I don't know, Albania or something. Seems interesting. Or anyways, result from linear combinations of the atomic orbitals. Orbitals? Bruh, orbitals. This is done by adding wave functions, which result in constructive interference, bonding molecular orbitals, lower PE. Subtracting wave functions, destructive interference, anti-bonding molecular orbitals, higher PE, less stable. So, when an s orbital and an s orbital collide, whoa. Hold on. What time is it? Oh, you're from Slovakia. I know Slovakia. The capital is Bratislava. If I go to Czech Republic, I would take a train and I would go to Bratislava as well. And then I would probably also go to Hungary. That would be sick. It would just be like a Central Europe trip. Austria, Czechia, Slovakia, Hungary. Orbitals? The craziest, the most Morbius chemistry class ever. Orbitals? Alright. So, for p orbitals, they do a little morbing. They do a little trolling, right? So we got px. So px and px, they do this. Bam. Py and py. Whoop. Pz and pz. Whoop. So this means, bam. That's sigma. Whoop. That's a pi bond. Whoop. That's another pi bond. Bam. Bonding results in something that looks like this. Anti-bonding results in something that looks like this. So pi bond. Okay, so now if you apply it, you do this and this and this and that. All right. Oh, fuck me. This is so complicated. So hydrogen gas, all right? Hydrogen gas. You got one S and one S because it's H2, right? So just a proton and electron, a proton and electron. And in these two orbitals, they combine head to head, so sigma, and they form a new orbital where the electrons, they go around both the hydrogen, but one goes around like bonding and the other goes around like anti-bonding, except psych, there's no anti-bonding because both the electrons ended up in the bonding one. This is where we have bond order. Bond order indicates the strength and length of the atom bonding. Higher order, stronger and shorter. Lower order, weaker and longer. All right, period 2, it just gets more and more complicated. So, oh my god. But you know, you get the idea, right? You get the idea. So, you know, got 2s and 2p. Only the valence, only the valence. So 2s down there, 2p, 2p, 2p up there. And then we fill in Hund's rule from lower potential energy to higher potential energy. Remember the Hund's rule, very important. And then like it's just like one big thing, you know, just finally chapter 9 is over. Amazing geographical knowledge. I salute you. Thank you. Well, I don't want to diss America too much. I know I've been a little harsh, but I don't know. I feel like, well, to be fair, an average Hong Konger would probably not know where Bratislava is, but like, I don't know. Anyone who likes geography by a little bit should know what the capital city of a country is. Just saying. Unless it's a very small, obscure country that not a lot of people has heard of. Like Timor-Leste or Sao Tome and Principe or something like that. Seychelles. St. Kitts and Nevis. Alright. Chapter 10, that's the final chapter. After this, I'm going to do a little small talk because my brain is melting. Chapter 10, Intermolecular Forces. So easy. So we got interparticle forces, you know, like ionic bonds, covalent bonds, metallic bonds, yada yada. IMFs, however, they're much weaker. So we got the three types. We got the dipole-dipole, so two polar covalent molecules, like HCl, you know. Dipole-dipole, my man, they're polar. So, you know, in HCl, obviously the electron of the H is attracted to the Cl. And then because Cl is more electronegative, so then the Cl is attracted to another H, you know, and so it's like, you know, wow, we're all bonded now, yay. Hydrogen bonding is more specific. It's either F, O, or N, so HF, H2O, or NH3. Or some other crazy compounds like NH4 plus or HO, you know, H2O2, hydrogen peroxide, something like that. London dispersion is the stupidest IMF ever because it's basically two non-polar covalent molecules, like, I don't know, methane. But why are they still bonding together like a bunch of idiots? Well, that's because suddenly, once in a while, some electrons randomly go to one side, breaking symmetry, causing a dipole moment. So for a moment, it's almost like it's polar. So suddenly the electrons are like, oh my god, it's polar. Let's bond together. Oh my god. Domino effect. So that happens. Yep. All right. So phase changes, you know, this is so easy. Suddenly it's easy again. So you heat something up, water, for example. It's ice. Heat it up, heat it up, heat it up. That's kinetic energy. And then transition from ice to water. That's potential energy. And then build up. And then another transition from water to steam, aka water vapor, and then you continue to rise. You know, Q equals to MC delta T, Q equals to N delta H of F, and Q equals N delta H of V. So N is number of moles. Viscosity, IMF higher, viscosity higher. You know, viscous liquids, like honey, like molasses, you know. Surface tension, so IMF higher, surface tension higher. Vaporization and vapor pressure, you know, surface area higher, rate of vaporization higher. So you've got a cup of water here, it's not going to vaporize until 12 million years later. But if you pour it and spread it out, Okay. Tomorrow morning, all gone. I mean, I'm in LA. This place is practically a desert. IMF higher, rate of vaporization lower, temperature higher, rate of vaporization higher. In a sealed container, there's no net vaporization because glass, liquid, and liquid gas. My brain, I'm damaged. I'm receiving brain damage from too much chemistry. Equilibrium vapor pressure is the pressure exerted by the gas above the liquid. It's the same. So, you know, nothing happens. Temperature increase, vapor pressure increase. If vapor pressure increases, this means they gon' vaporize. What can I say? Yeah. So vapor pressure is the amount of pressure. I need to look it up actually. Vapor pressure is the amount of pressure exerted. Shit. Let's just ignore it. I'll somehow find out tonight. So. T.I. molester. What? Say it. Okay, you know what? I've been streaming for 2.5 hours. I literally want to die. This is the longest stream I've ever done. This is the longest video I've ever done, in fact. Let's just do some small talk. You know what? Let's just go insane. Let's just go crazy. Go stupid. Go crazy. This is something that I've been meaning to do. It's how to socialize. First, get their Instagram at. Now that is very important because you know, if you want to socialize with someone, you got to establish a channel of a communication. Now not in the USA, in the uni life, people, they just come and go. You know, you don't stick with them. So back in secondary school, if you want to speak to someone, you can just be like, okay, see you next morning at school. I'll see you again, right? Yay. But in a university, in real life, that doesn't happen. I mean, even if you meet a classmate, these classes are usually weekly. They're not daily. So if you want to communicate with them, the best way to do it, Instagram app. Now, I'm no expert. In fact, I'm very much the opposite of an expert, but I'm trying to, I guess, write notes because I'm just so bad at socializing. Oh my God. This is what I learned. In fact, I learned this from JT. So JT is the half Thai, half Hong Konger who also studies in the same college as I am in. But for some reason, she's super popular. She's made 12,000 friends. But that's exaggerated. She made 200, 300 and something friends. Or at least she gained 300 and something followers on Instagram. Ever since she has arrived from January. That's less than half a year. That's insane. Why is she so social? I asked her, and she's like, well, you gotta DM them on Instagram. And I'm like, oh, Instagram, that's the answer. That's step one. And step two is very obvious. DM them. Interact. Find an excuse. If you get to UCLA, USC, best socializing club to join is Filipino club. Because all Asians literally join. Yeah, Filipino gang. I will, if I get to UCLA and USC, I will definitely join the Hong Kong Student Association. And not only like in the association, but I will try to get into the leadership team, okay? I am ambitious. I'm an ambitious boy. And what I'm going to try to do is I'm going to try to form collaboration, like diplomatic relationship with like Japanese student society and Korean student association and whatever. So maybe I can do something about that. Or maybe I'm being too ambitious. I'm just being too ambitious. That's the truth. I can't even make friends. How do I do any of this? Okay. Now, another thing I've learned is levels of conversation. So the first level is surface level. So surface level is literally What's your name? Where are you from? What's your major? How do you like LA? Stuff like that. Bullshit questions. Pleasantries. This is what you talk about when you meet a stranger. Now, the second level is a common experience. You meet someone and something happened to you too. It doesn't have to be anything traumatic. It can be, so I and Kelly, right? Kelly is someone from the church. Before April, we don't talk to each other all that much because every time we talk about things, it's just like, how's school? How's life? It's surface level. Until we went to a talent show in UCLA with Jonah. So the next time we meet up, we can talk about that talent show. It's common experience, and it's better to talk about. All right. Culture nights. I don't even know what that is, but I'm interested. I've been to UCLA how many times? Like the campus? I think I've been there 3 times so far. And UCLA is so huge. It's amazing. So, UCLA is like a whole district. It has so many streets and buildings. It has so much history. It has so many students. It has its own student governments and associations, and it's just a whole country in and of itself. It's so interesting. Honestly, UCLA, like if I get into UCLA, I want to just make a short film about UCLA. Like a documentary, more like a mockumentary, just about the history and the lore of UCLA and all the different associations and their diplomatic relationships, and make it super political for no reason whatsoever. It's just so interesting. It's like, it's just the lore. It's amazing. But I do know that the Hong Kong Student Association in UCLA does have these culture events where once a year they organize like a short film, not competition, but like, let's do a short film. I want to do that. And I know there aren't a lot of film majors in UCLA who are also Hong Kongers. So, if a Hong Konger like me get into UCLA film school, that's a W. That's a win. All right. Okay. Let's do something a little bit more advanced. I need to start thinking about how I socialize with people by thinking about how other people see me. I can be nice, but so what? I'm nice towards Pepper, right? When Pepper forgot to bring her pen to the class, I lend her my pen. And Pepper's nice to me, Pepper helped me multiple times. But being nice doesn't mean anything. And I'm not saying you should be a mysterious Sigma male. What I'm saying, though, is you should really flesh yourself out. You can be nice but still be boring. Like, you can be nice but be one-dimensional. If you're like a movie character or a TV character, you're just nice. You're just saying nice things. So what? But what you can do is flesh out yourself by joking around, be serious, be happy about something, be sad about something. This adds depth to your character and it makes you more trustable. And another advice I've gotten is just talk to people in a way where other people like to talk about themselves. So instead of just talking about your own experience, talk to them about their experience and comment on that. I'm such a loser. I can't socialize for the life of me, so I'm just like analyzing shit. Yes, character development. Honestly, I don't like categorizing people like you're deep, you're shallow, you're deep, you're shallow. Because everyone's got their own story. Everybody's got depth. It's just that some people show a lot of depth and some people don't. Some people purposefully hide it. Some people just don't. So, there's that. But I don't know, man. I don't know. I really don't. But yeah, Instagram is like number one best thing you can do. What to do if I don't have an Instagram and I don't want it because all I see in it is time sink and I get jealous of others easily. That's what happens to me a lot, actually. I have an Instagram account and I look at people and I get jealous because wow, you're having fun, wow, you're enjoying life. You're having a hot pot dinner. You're having karaoke, you're sleeping over, you're drinking, you're taking a selfie, you're partying, wow. But me, I'm in my bedroom, I'm studying, you know, like a loser, I'm just alone. But I think in the face of social media, I honestly don't know, but in the face of social media, you need to really like stand your ground and just I don't know, it's complicated really. There's no solution to this, actually, to be honest. If you have Instagram, if you have social media, you're just gonna see other people and it's just gonna be like, wow, good for you. I guess one thing I can do is to not compare myself with other people. So yeah, you can have 10 billion friends, but as long as I'm happy and I'm having fun, you know, so be it. Let's not compare. But I think what I'm essentially doing right now is to set goals. So level 2 friendship. So of course we have okay, JT, Potter, there's Pepper, there's so JT's gone, so let's cross her out because JT is too popular for me. Like JT has ignored me completely and she's gone. Potter's he's not talking to me a lot. See, this is another thing. Like I can be really nice to them and I can DM them from time to time, but just because of that, doesn't mean they're gonna like invite me to hang out. Unless I really flesh myself out in front of them. And I really make them feel comfortable around me. I think that is really the key here. Pepper is long gone. I'm sorry. Now we have Thomas, the Chinese dude, who I'm not particularly interested in being friends with because of the cultural difference. And even though he's Chinese, he's raised in USA, by the way. So there's a cultural difference, and not gonna lie, I did some stuff I thought I'd never do just to make friends when I was in uni. Wow. Okay. I don't know what university has in store for me, but All right, so Christian the Latino is a guy I met in Film 40. He's nice. He's chill. But then again, there's a cultural difference, but also I don't know, I just feel like and I don't want to box myself in, but I realize that I find myself more comfortable around East Asians. Maybe it's because they just look similar, but honestly, I don't know if uni does induce personality change, but secondary school definitely does induce personality change. Like, every single person I know, Natalie, Cedric, Leo, Pink, Mary, Jordana, Jeffrey, Keith, Kingsley, Ernest, Nick, all those people have changed drastically from the first time I met them in secondary school and the last time I met them. Including me, I've changed. So, yeah. So what ethnicities? Honestly, I feel more comfortable when I'm in front of Hong Kongers, I feel like. I'm sweating right now, Jesus. I'm gonna have to end off the stream soon because I've talked too much and I'm tired as hell and my brain is about to explode. But honestly, so in my college, is in West LA, and for some freaking reason, because it's West LA, for some reason, the dominant East Asian ethnicity is Japanese, which is awesome, by the way. So for some reason, my college has tons of Japanese students, and there's a whole group of, like East Asians. There's a whole EAS, East Asian Society. I was like that in the past, overthinking. That's true. I overthink. That's like my thing, I always overthink, even back in secondary school. But I feel like that's kind of a character trait of mine that will never really leave me. But sometimes I just try to not overthink. Like sometimes I would send a message to someone and that someone doesn't respond and I'm like, oh my god, did I offend him? Did I say something wrong? Or maybe he's just busy. Or maybe he's not. I don't know. Please respond. It's giving me anxiety. Maybe I shouldn't even care. All right. Okay, Christian. Okay, so first of all, Christian the Latino. He could potentially become my friend. I'm literally listing possible friends here. Okay, so that's one. Now, there's a very promising person called Kevin, who is a Hong Konger. And Kevin is, okay, so Pepper knows Spanish speaking friend, and his roommate is Kevin, who's also somehow coincidentally a Hong Konger. I haven't met him or seen him in person yet, but I look forward to do that after the final exams. And he seems like the type of guy who's also like me, socially awkward, so maybe we'll get along. Next person I want to hang out with, who is a very important person, is actually Aika, who is a Japanese girl from Script Writing Club, also film production major, somehow Pepper and her know each other. This again, okay, so let me just illustrate this for you. East Asian Society, EAS, a huge network of East Asians who may or may not know about each other depending on how popular they are in my college. And okay, I'm gonna illustrate this and then I'm gonna just take a shower and go to bed. Okay, so there's me. Okay, so I know Potter because I was introduced to him in February. And he's also a Hong Konger. I know Pepper because I coincidentally found her in my film class. So they're two separate people. I'm making a whole ass graph for this. Okay, and Pepper, she is a very social person and she has a bunch of friends. So she knows Aika, the Japanese girl. Let's put her right here. She has a Taiwanese friend, Taiwanese girl. And then there's a Japanese dude who's friends with the Taiwanese girl. And for some reason, this forms a whole loop. So the Taiwanese girl knows a Japanese dude, and then somehow Potter knows the Japanese dude, and he also knows the Taiwanese girl, and hung out with them. See, there's a network already. Okay. So I and Pepper and Thomas, the Chinese dude, are in the same film class. By the way, tomorrow is a Wednesday, and that's our final class. It's that film class. I'll be seeing Pepper and Thomas tomorrow night. Okay, and somehow Aika, me, and Thomas are also in the script writing club. And somehow Pepper also knows Aika. It's all somehow connected. Now, this is only a few people, but if you go to Instagram, I know it's really weird. It's really creepy too. But if you look at Instagram, which I will not tell you about too much, but they all know each other somehow. Like there's still like a vast network of people who just follow each other. And you realize that there's a whole network of them. They're everywhere. It's insane. So, yeah, I'm so tired. I'm just gonna stop the stream here. It's nearly 3 hours long. I will be doing a Spanish study session tomorrow night, by the way. So, all right, signing off. Culture Detective. Let's go.